Thanks. And thank you to the organisers for suggesting that it might be a good idea for me to come and talk about this. Last night, I rewrote my talk, having decided that I'd really tried to put too much into it. And so for those of you who were in the cryosphere session yesterday, you might have heard my co-author, Wouter Berghuijs, who's shown here in the picture, give a talk on this topic. And in effect, I'm going to give the same talk again, but from my point of view. So I don't think Wouter and I disagree about any of it. I'm just going to try and emphasize particular parts of it where people have asked me questions about this paper and said, well, what did you do there, or what do you mean by that? So I'm going to try and clarify some of those things. So the context for this work is the impact of warming climate on streamflow in snow-dominated catchments. We already know quite a lot about how warming impacts the seasonal distribution of river flows. So that's already quite well understood, and we don't really need to go through that in any more detail. The purpose of my talk is to think about, if there was warming, would that change the mean stream flow? Everybody expects it to change the seasonality, but what about the mean? Would the mean change? Now, until the start of 2014, most studies of warming in snowy catchment suggested changes in the mean flow could be neglected. There wasn't really anything interesting going on there. Why was it like that? Because there was no obvious mechanism for doing it and no convincing data that suggested mean flows would change. Wouter published this paper earlier on this year in Nature Climate Change. It makes three main points. That catchments with more snowfall as a fraction of total precipitation, they produce more stream flow on average, other things being equal. Second point, for any particular catchment, the years with more snowfall as a fraction of total precipitation, those years produce more stream flow. And the third point, this suggests that if a warming climate produces less snow, then there would also be less stream flow as a consequence. How did we do this? We looked at data from 420 catchments in the MOPEX dataset, about 50 years of data with daily precipitation, air temperature and stream flow. We calculated for each day a snow fraction, for which I'm using the symbol FS. This is, on each day, we used a simple temperature threshold method to assign that day's precipitation as either being snow if the temperature was below a threshold, 1 degree C, or rain if it was above that threshold. And so every day we have an amount of snow which is either some positive number or zero, and then we can sum up over a year or over the complete record and calculate a snow fraction. Of all the precipitation that fell, how much was snow? And there's a map there showing the long-term average values of FS that we calculated for these catchments in the US, values from 0 up to more than 0.5. We then took that data and analysed the long-term data, put it on a Budyko curve to remove the effects to look at the water balance and remove the effects of long-term average climate. So along the x-axis, we're plotting a dryness index, the ratio of potential evaporation to precipitation, and on the vertical axis, we're plotting the evaporative fraction, the ratio of actual evaporation over precipitation, or 1 minus the stream flow divided by the precipitation. And what we found was the snowy catchments, the ones coloured in red, tended to plot below the Budyko curve. And the snowier the catchment was, the larger that fraction of precipitation falling as snow was, the further below the Budyko curve the point plotted. And that's what's shown on the right there. So along the x-axis on the right-hand side, we've got how snowy is it, and on the vertical axis, how far below the Budyko curve does the point plot. So that suggests that whatever is going on here, the more snow there is, the stronger this effect is. This is only a correlation. At the moment, we don't know that snowiness is actually the cause why the water balance of these snowy catchments is different. So what we did was we now looked at interannual variability at each of the sites that were in snowy catchments. And the question we asked at each of those sites was, do snowier periods produce more stream flow? We studied 97 of those 420 catchments where the snow fraction was more than 15%, and we computed what we call the sensitivity of normalized annual stream flow to the snow fraction for that year. So if you imagine drawing a scatter plot, and along the x-axis there we've got the snow fraction for each year, so each symbol plotted is a different year, and on the vertical axis we've got stream flow for that year divided by the long-term precipitation, long-term mean precipitation. If you imagine fitting a regression line to that, if the slope of that line is positive, it suggests to you that more stream flow implies more precipitation. Sorry, more snow implies more stream flow. So if the slope of that line is positive, then more snow implies more stream flow. So we did that analysis. You also have to remove the effect of annual variations in total precipitation as well. But I won't go into the details of that, it's published in the paper. So we did that for 97 different catchments and worked out the slope of that line 97 times, and we found that for 94 of those 97 catchments, the slope of that line was positive. So that means if you look at between year variations in stream flow, the years with more snow produce higher values of annual stream flow. Why does that happen? We don't know yet. It's very tempting to ascribe a cause to that, but you can make a whole list of potential causes, and it's possible that different factors are causing this effect in different places because we're studying quite a wide range of different environments here. So I've put up a kind of laundry list of possible explanations there, which I won't go into in any detail. We need to examine a lot of those possible explanations, and there's still quite a lot of work to do to try and understand what's going on. Does it matter? Would it make any difference? Well, if you turn around that conclusion, if by studying different years we find that years with more snow have more stream flow, then that suggests that years with less snow have less stream flow. So now if you think about what happens in a warming climate, where we might expect less of the precipitation to fall as snow, then we'd also expect mean stream flow to be lower as a consequence, other things being equal. How big is that effect? Is it big enough that we should be interested in it? If you take a 2-degree temperature rise, for example, I'm going to do a kind of back-of-the-envelope calculation here. 2 degrees C temperature rise suggests from the MOPEX data a 35% decrease in the snow fraction. The average sensitivity to changes in snow fraction is about 0.29. So of that histogram over there, if you look at all those different sensitivities, there's quite a range of them from 0 up to about 1, and the average from that whole data set is about 0.29. So if we take that average sensitivity and we combine that with the decrease in snow fraction, then for a typical catchment, we get something like a 10% decrease in stream flow. But that's only an average statement. If you go to catchments which are more arid, or catchments which have very high snow fractions, the decreases could be more than 10%. They could be more like 20%, perhaps more. If you go to very humid catchments or catchments without so much snow, the effect is much smaller, maybe 5% or less. These are not specific forecasts for everywhere. This is just an average statement about the whole data set that we saw. The effect you see in any particular place could be quite different. Also, when we make these statements about change, we're assuming no change in total precipitation as well. So any of those changes would also have to be factored in. We're also assuming no changes in vegetation, for example. People have asked me several times, lots of really good questions about this. Isn't it obvious why this happens? It's not obvious to us why this happens at so many different places and why the effect is always positive. Most of the explanations I've heard are specific to particular environments, and I have no reason to doubt those explanations. Those people know those places really well, but I don't have any reason to expect that those explanations apply to other environments as well. It's even possible to make up stories and actually to see evidence about exactly the opposite effect. where streamflow goes down with increasing snow fraction instead of up. So there are some really interesting things going on out there that I don't think we really have a coherent story to tell about yet. People say, did you use the Budyko curve to get your result? And I would say no, that the Budyko curve results were simply suggestive. They said maybe there's something interesting, but it was the interannual analysis that really gave us something interesting to talk about, I think. People have asked questions about the PET data in the MOPEX dataset that come from a national monthly potential evaporation atlas. Don't the doubts about that data invalidate some of our conclusions? Well, for the interannual analysis, we didn't use any of that data, so I don't think that's a critical problem. Some people asked if this is a trading space for time argument about the effects of climate change, and I'd say, no, because we rely on the interannual analysis, then what we're in effect doing is we're extrapolating from past temporal variation into the future and making a bunch of assumptions. And of course, people ask us to explain figure 2 again, but I've had one go at that already today. What will we do next? There's more data analysis to do. We need to expand our geographic coverage. I'll show you a little of that in a minute. We also need a more detailed examination of these streamflow reductions when snowfall goes down. At what time of the year is that water being lost, or at what flows? Is there any pattern or structure to that, or is it just an effect that's happening all through the year? We haven't looked at that yet. We also need much more insight into the mechanisms that could be behind this. If this is a real effect, then we actually need to know why it's happening before we can do anything useful about it. So one obvious place to look is in the existing multi-year field studies that show variations in water balance between snowy years with more snow and years with less snow. The observations of water fluxes and water storages from those basins would be very useful and very interesting to try and reveal, well, do those studies have anything to say about this question? The other place to look is in simulation models. If you analyze the output, the streamflow output from a simulation model of a snowy basin, do you find the same effect? Which models show that effect? Do they all show that effect? And if they do, why do they do that? If we look inside the model, if you treat the model like a field experiment that gives you some idea of what's going on in different places, maybe we can use that to make suggestions about which mechanisms are behind this. Here's some initial results from the study we did in Austria, and what we found was, in effect, much the same thing again, that we found that this figure 2, this histogram of what the slope of those regression lines look like, shows that, again, most of them are positive. So in most of the 60 basins in Austria that we looked at, we found that there's a positive association between streamflow for the year and the snow fraction for that year. Okay, so this is my last slide. So just re-emphasize the 3 main points again. Catchments with more snowfall produce more streamflow, other things being equal. For any particular catchment, years with more snow produce more streamflow. And this suggests that in a warming climate, if that produces less snow, it may also produce less streamflow on average. These snow-fed catchments are water towers for society, so understanding how they work is really important. And the fact that I didn't see this coming, I was taken by surprise by this analysis, suggests that maybe I have quite a bit more to learn about how climate and catchment characteristics control the water balance in these kinds of catchments. Thank you very much.
We can take one quick question. Only one. So the gentleman, oh, yeah.
Just a quick answer. At least some of the hydrologic simulation models very clearly show less runoff if you raise temperature. And if you look at in the entrails of the model, it's due to increased evap losses. Then didn't even get to the point of trying to look at year to year and snowiness fraction. So that's probably just the partial answer. Your question is even more fascinating.
Okay, thank you.
Thank you, Ross.